In the last video, we explained if you take a bowling ball and you drop it in a container of water, we explained how that bowling ball is going to sink and it's going to be fully submerged in that container of water. And we explained that happens because this bowling ball is more dense than this water solution. So whenever an object is more dense than the solution, then that object fully submerges in that fluid. However, in this video, I want to talk about an example where we have an object that's less dense than the fluid. However, to understand this, you really need to understand the previous video, so I have a link of that video below. And unless you watch that video, this video won't really make sense. So let's try another example. Let's say we have this rubber ball with a relatively low density. What happens if we drop this rubber ball? Well, we know it's going to drop, and it makes sense that it's going to float in this water solution. However, it's going to drop a little bit, so therefore, because it drops a little bit, it's going to raise the water up a little bit. So therefore, we have these two forces battling. The force of this rubber ball wanting to drop, and the force of this displaced fluid wanting to drop. This displaced fluid has mass, so therefore wants to drop, and this ball has mass, so it wants to drop. So we have these two forces battling one another. But something important to realize is if this ball falls, part of it's going to be submerged. So let's say 0.0006 meters cubed volume of this ball has been submerged. If this volume of the ball has been submerged, therefore this volume of water is going to be lifted upward. Because where did this volume come from? It came from this volume of the ball that's been submerged. So therefore, if this volume of the ball that's been submerged was 0.0006 meters cubed, therefore, the volume of displaced water that's been lifted up is 0.006 meters cubed. The volume of the water that's been lifted up equals the volume of this ball that's been submerged, because that's where this volume came from. It came from the volume of the ball that's been submerged. So hopefully that's logical and pretty straightforward. So if we just let this ball drop and we just leave it alone, we know it's going to drop, it's going to lift up some water, then this water is going to drop, it's going to lift up the ball, and eventually we're going to reach an equilibrium. And when we reach an equilibrium, the ball is going to be stationary and it's going to be floating. So now that this ball is stationary and floating, we can analyze the forces that this ball is feeling. So again, this ball has mass. So because it has mass, we know it has a weight. Anything with a mass has a weight. So it feels a force downward due to its weight. However, there's a certain volume of water that's been lifted up. There's a certain volume of water that's been lifted up, and this volume of water that's been lifted up also has mass. Because it's water, so it also has mass. So it also feels a force wanting to go downward. So as this water that's been displaced and it's been lifted upward, this water has mass, so it also wants to go downward. It wants to drop to a lower level. So as this water that's been displaced upward, as it applies that force going downward due to its weight, it's going to lift this ball upward, like we've explained earlier. So that force of this ball feels upward, that's the buoyant force. That is the buoyant force. So this ball, once it's stationary and reached that equilibrium, it's going to be feeling that buoyant force going upward. Because again, this water has mass, so therefore it wants to drop, so it's going to want to lift this ball upward. So therefore we can see as this ball drops, it'll eventually reach an equilibrium. And once it reaches an equilibrium, it feels two forces. One, the force due to its mass, its weight. So it feels a force due to its weight, that's straightforward. And also remember, it's lifted up some fluid. Some fluid's been displaced and lifted up. That water isn't happy. It wants to go down to a lower level state. And as it applies that force downward, it lifts the ball up. So this water that's been lifted upward also wants to go downward, feels a force downward, and that's going to apply buoyant force on this ball. So now we know the two forces this ball is feeling. Once this ball reaches an equilibrium and is stationary, it feels two forces, the force of its weight downward and the buoyant force upward due to this water wanting to go down. So now in this example, something really important to realize in this particular example is this rubber ball is floating. It's floating, it's reached an equilibrium, it's stationary, and it's floating. So because it's floating, it's not moving. It's not moving downward and it's not moving upward. So it's reached an equilibrium. So therefore, if it's not moving, therefore we know the force of the weight of this ball must equal this buoyant force going upward. These forces must equal, and that's why the ball isn't moving and it's stationary. So therefore, we know the force of the weight of this ball must equal this buoyant force. So once this ball reaches an equilibrium and is floating, we know the force it feels downward due to its mass has to equal the force of this particular amount of water that's been displaced wanting to go downward, applying a buoyant force. Those two forces must equal each other, like we just said. So therefore, we can compare these two forces. If we know the mass of this ball times the acceleration due to gravity, we can determine the weight of this ball going downward. If we can determine the mass of this water that's been displaced and lifted upward, if we can determine the mass of that water and multiplied by the acceleration due to gravity, we can determine the force that this water feels downward, and therefore we can determine the buoyant force, because that's where the buoyant force comes from. But remember, in fluid mechanics problems, rather than dealing with masses, we like to deal with density times volume. So therefore, this also equals the force that the bowling ball feels downward. And this also equals the force that this water feels downward. And therefore, it also equals this buoyant force. So this equation also equals the buoyant force. So again, this is the density of the ball. This is the volume of the ball. This represents the density of this displaced fluid, and this represents the volume of this displaced fluid. Because again, if we know the density of the displaced fluid and the volume of the displaced fluid, we can determine the mass of this displaced fluid. And if we multiply it by acceleration, we can determine the force that this displaced fluid feels downward, and therefore determine the buoyant force that this ball feels upward. And remember, these two forces equal each other because it's reached an equilibrium. So this force the ball feels downward equals the buoyant force it feels upward. And that's why it's not moving. So therefore, these two forces must equal each other. So this is the most important part of the video. So realize this rubber ball has a constant mass. Its mass isn't changing, so therefore it has a constant weight. So let's say it has a weight of 60 newtons. So that's the force of this ball feeling downward. So therefore it's going to fall, and as it drops, it's going to lift up water. And it's going to lift up the exact specific amount of water that has the specific amount of mass that gives it a weight of 60 newtons. So the weight of this displaced water will be 60 newtons. Because we know it's eventually going to reach an equilibrium, and in that equilibrium, the weight of this ball going downwards equals the weight of this displaced water going downward, which equals the buoyant force, and we're going to reach an equilibrium. So therefore, the point is, whenever you have an object that drops in water, it's going to have a certain mass and it's going to have a certain weight. So it's going to drop, and it's going to lift exactly that same weight of water up in the air, and it's going to reach an equilibrium where the weight of the ball going downwards equals the exact amount of water that's been lifting up. So this exact amount of water has the same weight as this ball. And hopefully that makes sense. And maybe the ball isn't the same density as the water, so therefore this volume of the water maybe won't be the same as the volume of this ball. But that's not what's important. What's important is to realize this ball has a weight. So it feels that weight downwards. It's going to lift the exact right amount of water until it lifts up the exact right amount of water that has the same weight as whatever the weight is of this ball. So now the weight of this water going downwards equals the weight of this ball going downwards. So therefore, we're going to lift exactly the right amount of water so it has the same weight as this ball. So again, remember, a key point is to realize the force that this ball feels downward the force that this ball feels downward equals the force of this displaced water going downward. These two forces equal each other. And that's why the ball is stationary and it's floating, it's not moving. So remember, we can quantify the force that this ball feels downward by using this equation, the mass of the ball times the acceleration due to gravity. And we can quantify the force that this displaced water wants to feel downward by using this equation, finding the density of the displaced water and multiplied by the exact volume of this displaced water, which again equals the mass of this displaced water and multiplied by the acceleration due to gravity. And remember, this force of this ball going downwards must equal the force of this displaced water going downward. These forces must equal each other, and that's why the ball isn't moving, because the force that the ball feels downward equals the force that this water lifts it upward, and that's why it's not moving. So these two forces equal each other. However, we know the acceleration due to gravity is constant, so we can just cross out these g's. So now we're left with this equation. The density of this ball times the volume of this ball equals the density of water times this particular volume of this water that's been lifted up. Now, just doing some algebraic rearrangements, we can divide both sides by the volume of the ball, canceling this out, and divide both sides by the density of water, canceling this out. And if we do that to both sides, we're left with this equation. So I just did some simple algebraic rearrangements. Again, going back, we went from this, just simply rearrange it, and now we have this. So now we're left with this equation. But this equation tells us something really interesting. So remember, this volume, this is the volume of this water that's been lifted up. Remember, you can go back and remember this volume was the volume of this water that's been lifted up. But remember, we already said earlier, the volume of this water that's been lifted up equals the volume of the ball that's been submerged. And I know this is a little tricky, maybe you have gotten lost, but if you go back, we've already explained what this volume term was earlier on. We explained what this volume term was. And we already explained that the volume of this water that's been lifted equals the volume of this ball that's been submerged. We already explained that. So if this equals the volume lifted, which equals the volume of the ball submerged, therefore this equals the volume of the ball submerged. So go back and rewatch that if that was confusing. But again, this equals the volume of the ball submerged. This equals the volume of the ball submerged. If you go back, remember this V term, which was over here, we said this was the volume of the ball, the total volume of the ball. So we're left with this equation. This equation is pretty interesting. This equation essentially tells us that the ratio of the density of the ball divided by the density of this fluid equals the volume of the ball submerged divided by the total volume of the ball. And this is an important equation. The percentage of an object submerged, which is what this is, the volume of the ball submerged divided by the total volume of the ball, is the percentage of the ball that's been submerged. Again, the volume of the ball submerged divided by the total volume of the ball tells us the percentage of the ball that's been submerged. That will equal the ratio of the density of the ball divided by the density of this fluid. So this is just an important equation. This is essentially the derivation, but you may see this in a physics class or on the MCAT. So this is an important equation to be familiar with. For example, we said the density of this ball was 600 kilograms per meters cubed. We know the density of water is 1,000 kilograms per meters cubed. So this gives us 60%. So therefore, we know the volume of this ball that's been submerged is 60%. This is the volume of the ball that's been submerged, and this is the total volume of the ball. So if the volume of the ball that's been submerged was 0.0006 meters cubed, and the total volume of the ball was 0.001 meters cubed, then this tells us the volume of the ball submerged. So again, the ratio of the density of the object divided by the density of the fluid tells you the percentage of the object that will be submerged. I'll say that one more time. The density of the object divided by the density of the fluid that it drops in will equal the percentage of the object that will be submerged. In this example, 60% of the object will be submerged because this is the volume of the object that's been submerged, and this is the total volume. This is the total volume of the object. So this is an important equation to be familiar with, and it is essentially, if you have the density of any object and the density of any fluid, you can use this equation to determine the percentage of that object that will be submerged. So again, this is an important equation you need to know for the MCAT. If you know the density of an object and divide it by the density of the fluid that it falls in, that ratio will tell you the percentage of the object that will be submerged. So if this ball has a density of 600 kilograms per meters cubed and the water has a density of 1,000 kilograms per meters cubed, this would give us 60%. So therefore we know 60% of this ball will be submerged. This is 60% of the total volume of the ball will be submerged. However, one exception is if the density of the object is greater than the density of the fluid. Because if we did an example where we have a bowling ball which has a higher density than water, and if we use this equation, what would we get? Well, we know the density of this bowling ball is greater than the density of this water, is greater than the density of this water. So because the density of this object is greater than the density of this water, this ratio will give us over 100%. But it doesn't make sense that over 100% of this volume will be submerged. At max, we can have 100% of the volume submerged, but we can't have more than that. So this equation maxes out at 100%. But this already confirms what we learned earlier. We learned if the density of an object is greater than the density of the fluid, then it will be fully submerged. It will 100% be submerged. And that's what this tells us. This equation maxes out at 100% of an object being submerged.